look at that. For example, we have a Hamiltonian like that. This is the Hamiltonian general. This is a general Hamiltonian for n particle in 3 dimension. So I can make a summation over that. So I can make a summation from 1 to 3n xi partial xj. Oh, not now, later. So this is the Hamiltonian. So you can use this Hamiltonian and calculate different expectation like qi partial and qj. What will be that expectation value of partial derivative of this with respect to qj? So it will be sigma r1 to 3n. This is a constant. r partial qi square over qj. Will be sigma r1 to 3n. Expectation value qi, and this is constant. What is the partial of that? 2qr partial derivative of this with respect to qj. 2 sigma r. That was the question for the midterm last semester. I give this Hamilton and ask him to calculate the partition functions. Just making the derivative was the question. Okay. What does it mean? That delta A, R and J. If R and J are same one, otherwise it's that's very interesting because it gives you R should be J. Sorry, J should be delta Rj. Delta Rj, yes, delta Rj I have here. It gives you R should be equal to J, so 2Rj and you can repeat that for the pi partial derivative of that with respect to pj. Almost the same, so almost all the steps the same, just with the 2bj pi pj. Especially when I is equal to j, especially when I is equal to j, so this term will be quadratic. This term will be quadratic, and the quadratic terms, it looks like the harmonic oscillator. In harmonic oscillator, you remember we showed that the expectation value of the kinetic and potential energy are half. That will be the same. So if you make I equal to j here, so you will get qi partial h with respect to qi equal to 2ri. Expectation value of qi is here. And that will be, what does it mean? It will be kBt, kBt, because I is equal to j. And now if I make a summation over this from I1 to 3n, I will get just sigma I1 to 3n of this expression. Will be 3n kBt, and the same will be So, you know what is that? AJJ2 is the kinetic energy in this Hamilton. So 2 average kinetic energy will be 3n kBT. If you remember that, and 2 potential energy will be 3n. You remember what was that? In the holiday. In holiday Resnick, you calculated in chapter 20, I think, or 20. In chapter 20, you have it to call it kinetic theory of gas. You calculated kinetic energy average, 3n over 2 kBT. And this is comes from here. And this is I don't know, I want to think that how this theorem is powerful. We started from very general Hamiltonian. And this Hamiltonian described the three-dimensional motion of the n particle. And but if you have something here, what happened, for example? What you think if we have a Hamiltonian like that? I think this week you will have I will give you one homework, but it will come not this week, next week. So you have almost 2 weeks to think. So if you have that, what happened? Something like that, you know? It looks like there's some interaction between the momentum and the position, no? Like the magnetic fields, for example. You know, the normal force gives you the energy like q squared or p squared. This is a q dot p, so p dot r, something like that. P means that velocity. So this term looks like r dot v, and it looks like b dot. Yeah, B dot V, for example, if the B is the magnetic field, or even can be electric field, something like dipole interaction or something like that. Even for this Hamiltonian, you will do, I will do that like a homework. You will work in this Hamiltonian, and just repeated that. I want to know that what's the rule of this term. If you have the interaction, what will happen? And you will see that the contribution to the term 1 is 0, the term 1. So you don't need to care about that. So I just finished the partition theorem, but the virial remains. So virial we do next lecture. Thank you very much.